Hi, hello there, and welcome back to Steamer with Steve. Today we're going to go through how decimal place values work inside of this number system. So let's jump on in. So place values are really important inside of our decimal number system, as without that you don't necessarily know where things line up. So to begin, what we're going to do is we're going to understand the basic concepts within inside of place value, then learn how to convert between decimals and the scientific notation. We're then going to identify and work with repeated decimals and see how they look, and then perform some real basic operations within the decimals. So just pause the video, have a go, see if you can rearrange these into ascending order. Cool. So what we should have done is you should have put the 0.057 first, then the 0.55, then the 0.57, then 0.75, 0.77, and then 1.57. My hint to you is as you just scan across, find the smallest one and then take it out. So cross it throughout and then keep scanning through each time. Cool. Now, before we get into Roman numbers, into decimal places, we're going to go through how the Roman numeral system works. Now, this is deeply intertwined with how our number system works, and hopefully you will pick up the pattern of why our number system is built based off this. So the Romans had this really cool number system where they had in groups of fives or tens, and basically you would either have I as 1, V was 5, X was 10, L was 50, C was 100, D was 500, and then M was 1,000. Now, you would use these letter combinations together to make the numbers that were in between it. So, for example, 2 was just II, 3 was III, and then, this is where it got a little bit different. Instead of writing III 4 times for 4, what you would say is 1 before V. So IV, which would then be 4. Then if you went VI, that would be 6. And then VII would be 7. VII would be 8. And then again, IX would be 1 before 10 or 9. And then you'd go up to 10. Now, this pattern was really handy, right? So basically, what you can see here is instead of having 4 characters, you've done it in 3 characters for 3. And they're just pretty simple characters because it's just I and V. And then basically once you go up to 4 characters here with VII, instead of going VII, you could just go 1 before X. And then that pattern would repeat. So instead of, if you went to 10, you now have got 1 after 10. And then this is sort of like your tens column. So you got X all the way up to 20, which is XX. And then you could do stuff like this. So, for example, 26 is XX, which is like your tens column, and then VI, which is then the same as 6. So just pause the video, have a go at these ones, and try and convert. Now, if you get super stuck, there is a table here with all the numbers on it that you can sort of play around with and get used to it. Awesome. So the first one, XI, is 11. XXII is 23, XLIV is 44, and then LXXVII, so that's LXX is 70, and then VII is 8, XC is 90, and then IX is 9, so that's 99, and then going the other way and converting it to Roman numerals, 8 is the same as VII, 42 is the same as XLII, 73 is the same as LXXII, 89 is the same as LXXXIX, and then 475, a little bit harder, is CD, so it's 100 before 500, which is 400, and then LXXV. Now, hopefully what you've picked up here is it's kind of got this similarity between our current number system. It's a little bit different, but it still has the hundreds, and then the tens, and then the ones column sort of connecting it. Now, there's a whole heap of different number systems that exist out there. So the ancient Egyptians used hieroglyphics, which is kind of cool. So a pharaoh is worth 1,000,000 because I'm guessing it's worth 1,000,000 people. And then you've got a candle is worth 10,000. And then you've got the whip is 100 and all these different stuff. And a parrot is the same as 100,000. But then they actually included reciprocals as well. So they had fractions, which is kind of neat. So to combine 2,000, for example, you would do 2 of the staffs and then 1 of the little dashes all the way through. And that would allow you to connect it, which is kind of cool. So The Mayans then had another number system where they used dots, and I'm pretty sure they did it as hands. So 1, 2, 3, 4, and then 5 was considered a hand. And then each hand basically stacked up underneath. So 15 was the same as 5 hands, 10 was the same as 2 hands. And then the other cool thing is they had the first symbol for 0, which is this sort of flattened out football here. Then you've got your Chinese number system. So you've got 1, 2, 3, which looks kind of similar, except sideways. Then you've got your 4, 5, 6, 7, 8, 9. And then a 10 was just an X, which is kind of like Roman numerals as well, which is kind of cool. And then 100, thousands, and then 10,000s. And then obviously the million looks a lot more complicated. I'm sure there's some sort of story behind that. The other one that I found, which was kind of cool, is this sister scene digital scoring system that medieval monks used to use. And what it had was these 4 quadrants. So in quadrant on the top right-hand corner, you had your ones column with all these different symbols. So for example, a triangle in the top right-hand corner gave you a 5. Then you had your tens column up in the top left-hand corner. Then you had your hundreds column in the bottom right-hand corner. And then your thousands column in the bottom left-hand corner. And then you could write a really complicated number. So for example, 1,993 was this. So the 1 came from this column, 1,000 down here. So that's why it's a 1 there. The 99 is the box. So each time you saw a box in each of those quadrants represented something. And then the 3 was the little tail coming down like that, which is kind of cool. So you could write numbers from 1 all the way up to 9,999 in this unique sort of little shape, which is kind of cool. So the history of how our modern number system actually works is kind of neat. Actually comes from India, so the Brahmi system. And if you remember back to the Chinese characters, it looks somewhat similar as well. So they had the 1, 2, and the 3 dashed across like this. Then what happened is the Hindus took over with that system, and then they've introduced 0. And they made the numbers a little bit more different. So the 1 was still a 1 dash, it looks like. And then the 2 had the 2 dashes, and the 3 had the 3 dashes there. And just slowly sort of evolved, which is kind of neat. The 5 looked a little upside down there. 6, I'm not quite sure how that evolved, but that was kind of neat, and so on. And then the Arabic system took the Hindu system and then changed it around again. So instead of the 1 being that way, it's now this way. The 2 had the little squiggle, 3 had 3 squiggles, 4, 5, 6, and then 7 was upside down. The 8 was the other way around, and the 9 still was sort of the same. And then we had the medieval system. So this looks a lot more similar. So 0, 1, 2, 3. 1 looks a little bit Roman, but that's kind of cool. The 4 looked like a fish upside down. The 5 was also upside down. 6 stayed the same. 7 was a little flattened. And then we have our modern number system looking like this, which is kind of cool. So the whole point with this is these symbols are just representations of what is in each of those place values. So how many characters are there in our modern number system? Well, hopefully you know this. There's 10. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And then 10 is a combination of those different characters. So you have all these ones through here. And then why do we count in groups of 10? Well, it's pretty simple. The answer is right in front of you. You have 10 fingers. So humans count in groups of 10s. And you should have picked up on that pattern all the way through history. So, for example, the Roman number system had 5s and 10s. Mayans had groups of 10s. The Egyptians, and then the Chinese characters number system as well. So the answer is right in front of you. So if we had 8 fingers instead, we would probably count in groups of 8 instead of 10, which is kind of cool. And if you do computer science, you should know binary as well, which counts in groups of 2. But that's a little bit more complicated and way beyond the scope. So the way our number system works is you've got your 1s, 10s, 100s, thousands, and then 10,000s. Or another way of thinking about it, if we'd use powers, this column here is the same as 10 to the power of 0, 10 to the power of 1, 10 to the power of 2, 10 to the power of 3, and then 10 to the power of 4. So if we wanted to work out this number and break it down into place values, we would go through and do the timesing. So 0 times 1 gives you 0. 4 times 10 gives you 40. 1 times 100 gives you 100. 9 times 1,000 gives you 9,000. And then 4 times 10,000 gave you 40,000. So if we add all that together, you get the number that we were looking at. So why do we learn number systems? Well, the importance is we understand how decimal concepts work in fields like science and engineering, and it helps a heap when we try to understand those packages when we get there. So have a go at this. So if we wanted to unpackage 3,574 and 9.982 into the different columns, we can literally place them in each of those pieces. So the ones is where I usually start, and you should see it's nice and symmetrical over this decimal point. So you've got your units, and then you've got your tens, tenths, hundreds, hundredths, thousands, thousandths on the end. So the 4 goes there, then the 7, then the 5, and then the 8. Then for the tenths, the 9 would go there, the 8, and then on the end you should have the 2. Now if we wanted to unpackage that further, we have 4 lots of 1 there, 7 lots of 10 there, 5 lots of 100 there, and 3 lots of 1,000 there. Then for the tenths column, we've got 9 lots of tenths, 8 lots of hundredths, and then 2 lots of thousandths. So then to run out the actual value of this 3, it's not 3, it's actually 3. With the 4, let's start there, it would be just 4. The 7 is not 7, it's worth 70. The 5 is worth 500, and then the 3 is worth 3,000. Same with over here, the 9 is not just a 9, it's actually 9 tenths. The 8 is actually 8 100ths. And the last one is 2 is the same as 2 1,000ths, which is kind of cool. So have a pause of the video, and what I want you to do is compare these two numbers against each other and then look for the similar place values within. Cool. So what you should find with the first one is you've got the 5, the 3, the 7, and then the 2. And then on the tenths, you've got the 7, the 8, and then the 3. So then the 5 is the same as 5 lots of 1, 3 is the same as 3 lots of 10, 7 lots of 100, and then 2 lots of 1,000. Then the 7 becomes the same as 7 times a tenth, 8 becomes 8 times a hundredth, and then 3 becomes 3 times a thousandth. So then we've got a 5, we've got 30, we've got 700, and then 2,000 is the actual value of those numbers and those place values. And then on the other side, we have 7 tenths, 8 hundredths, and then 3 thousandths. Then, if we do exactly the same with the other one, so we've got a 5, we've got a 7, a 3, then a 2, and then we've got a 9, and then a 3 in the thousandths column. Then we've got 5 lots of 1, 7 lots of 10, 3 lots of 100, and then 2 lots of 1,000. Then over here, we've got 9 lots of tenths, 9 lots of hundredths, 3 lots of thousandths. So then if we fill in the blanks, we've got 5, we've got 70, we've got 300, and then we've got 2,000. Then on the other side, we've got 9 tenths, 9 hundredths, and then 3 thousandths. So if we compare, we might get a little confused because we've got a 7.3 and a 3.7. They're not exactly the same value. So this is 730 and this is 370. So the 2,000s are the same in both the numbers. The 5s are the same. The tenths are not the same, and the hundredths not the same. But then the thousandths have exactly the same value in them. So that's another way of thinking about the place value here. So just pause the video and have a go at these ones here. Cool. So what you should have found with the first one is 36.485 is less than 37. 21.9, so that's going to be greater than. 0.0372, so that's going to be less than. 4.217, so 17 is going to be less than 18. 65 straight away, that's going to be greater than. And then 9.52813, and then the 5, so then that's going to be less than based off the place values. That's right. This side's going to be greater than that. Then we rearrange these sets. So they want them in descending order, so from biggest to smallest. So going across, it looks like the 3.6521 is the biggest. Then you got the 3.625. Then you've got the 3.256. Then the 3.229. Then the 2.814. And lastly, the 2.653. Then these ones through here, starting with 11. So 11, 9, no, 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 no. Yep, that's bigger. So 11.908, then 11.907, then 11.898, then 11.891, 11.875, and the last one's 11.799. Then these ones here, the 1.326, then the 1.305, 0.8202, 0.765, 0.043, and then 0.039. And the last one, which of the following of the mixed number is equivalent to 8.17? So 8, if we've got that. And then 17 would be the hundredths. So not the thousands, because that would be 8.017. Yeah. Cool. Then converting these ones fractions to decimals, just pause the video and have a go. So hopefully you've seen that these are going whole amounts. So this is the same as 2 lots and 39 over 100. So then that's the same as 2.39. And then this one over here, you would multiply both the top and the bottom by 4. So you get 36 on 100, which then is the same as 0.36. Then rearrange these orders, the smallest to largest. So the first one, you got 3.410, 3.412, 3.415, and 3.4155. Convert to decimals, so 3.4 is the same as 0.475. And then 5 on 9 is the same as 0.555555555, repeating on and on forever. So that's another topic that we need to deal with a little bit later. And then convert the following into fractions. So 25 over 100 is the first one, which then simplifies down to a quarter. And same with this one is then just 61 over 100. Cool. So there is a Dr. Frost attached to that. Have a go. Hopefully that's giving you some insights into the different aspects within inside of how place values work. Now, the more you play with them, the easier they become. And hopefully you've seen the really cool link between Roman numerals and then also the decimal values based on the groups of 10 based off our fingers. So if you've enjoyed this video, please do give us a like and subscribe, and also sign up for the notifications for any of the new content that I'm going to be trying to pump out. It does help with the YouTube algorithm, and it really does help trying to get that message out there for math is available for everyone. If you do have any questions as well, please put them in the comments down below. That's it from me. Thanks again, and see you next time on Steam It with Steve. Adios.